So welcome to the next lecture on parameterized algorithm. Today we continue our work with Treewidth. You should see now the second the next batch of lecture notes. So let me start with a recap what was happening last week. So we were looking at the notion of treewidth and of tree decompositions. We defined it in two different ways. The first, maybe more intuitive definition was via this notion of tree embeddings. The idea was that if we've got a graph G, then we would like to somehow understand the structure of this graph by embedding into a tree. So here we've got a tree T, and we would like to think about tree embeddings. And a tree embedding is a mapping that maps every vertex of a graph, for instance, this blue vertex, to a connected subtree in the tree. And the rule is that whenever we've got two vertices that are adjacent in the graph, the two subtrees representing them in the embedding should connect. Should intersect. So this was the notion of tree embeddings, and this notion was equivalent to the notion that we usually were using for the purpose of working with treewidth and tree decomposition, namely the notion of tree decompositions. So a tree decomposition is a tree together with a back function that assigns to the nodes of the tree subsets of vertices that are called backs. So the picture is like that, and the idea is that this back structure should somehow represent the structure of the graph. So for every edge in my graph, there should be a node whose back contains both the endpoints of the edge, and for every vertex of the graph, whenever I look at all the backs that contain this vertex, they should form a connected subtree of my tree decomposition. And these two notions were equivalent in the sense that if you have a tree embedding, then you can create a back function by looking which subtrees contain a node of interest in my tree. And on the other hand, if I have a tree decomposition, I could always project it to a tree embedding by just assigning to every vertex of the graph the set of all the backs, all the nodes whose backs contain this vertex. So then we define the width of a tree decomposition as the maximum back size minus 1. And the treewidth of a graph is the minimum possible width of a tree decomposition. And this roughly corresponds to how well I can understand the structure of the graph in the structure of a tree. Yeah. And this notion was helpful as a sort of auxiliary structural parameter for algorithmic purposes. So we've seen various dynamic programming algorithms based on tree decomposition. So they usually work by sweeping a tree decomposition bottom up. For instance, the maximum independence set problem we could solve in time 2 power k times some polynomial in k times linear in the size of the graph. We also have seen Kurzweil's theorem that gives you a generic way of obtaining such dynamic programming algorithm from a formulation in monadic second order. So what we finished with the last time was that this problem of computing a tree decomposition of a graph. So we said that computing the tree with exactly is hard. However, it is FPT parameterized by the target width. The algorithm for Budlander works in time 2 power order of k cubed times linear. This is the algorithm of Budlander. What we will now show is a constant factor approximation algorithm working in running time 27 power k times n squared, roughly. And this algorithm is an approximation algorithm in the sense that it is given this number k, which is the target width, and it either concludes that the treewidth is larger than k, it tells no, the graph is too complicated for me, or it gives you a tree decomposition of your graph. However, the width of this decomposition may be slightly larger than k. It will be width at most 4k plus 4. Right. So this is our goal for the first part of the lecture. Are there any questions at this point to this one?
If we get the tree decomposition, do we know that the actual tree width is less than or equal to k, or do we just know that it's less than or equal to 4k
We
plus
don't
4?
know. We
Okay.
know that it is, of course, at most 4k plus 4 because we have a tree decomposition to witnesses. But in case the tree width is, for instance, equal to 2k, the algorithm can give both outcomes. It may succeed in actually computing a tree decomposition. So it is not a decision algorithm for tree width. Good. So we will be working mostly with sort of separability, properties of tree, and for this, let's start with some baby case, namely the case of a tree. So there's a very well-known lemma about trees, about the existence of a so-called centroid in a tree. So a centroid in a tree is a vertex of the tree, say U, such that whenever I look at every component of the tree after removal of this vertex, this component has at most half of the vertices. So for instance, in this tree here, this should be a centroid because whenever you are looking at a connected component after removal of it, this component has at most half of the vertices. Yeah? So I claim that in every tree there is such a centroid vertex. And the proof is actually very simple. So whenever I'm looking at a edge of a tree, this edge splits the tree into two parts, right? The left part of the tree and the right part of the tree. So let me now look which part is larger in terms of the number of vertices, and I will orient this edge in the direction of the larger endpoint. Yeah. So in this way, if I do this for every edge of the tree, I get an orientation of the tree, right? So in a tree on n vertices, I have at most n minus 1 edges. Yeah. So after orientation, there are at most I have exactly n minus 1 edges. So after orienting those edges, yes, I have n minus 1 tails of those edges. However, we've got n vertices in total. So there must be a vertex here, the central vertex here, yeah, which is not a tail of any edge in my tree after orientation. So let's look at this. Let's look at this vertex. Whenever I look at a connected component of the tree after removal of this vertex, yes, I decided to orient this edge towards this vertex, which means that this part must have been the smaller part, in particular part that has at most n half vertices. Yeah, because every smaller part has at most half of the vertices, and similarly for all the other parts. Yeah, so this vertex with out degree 0, yes, is a vertex that indeed has all the properties that we need. I forgot to say that if both of the sides are of size exactly n half, I orient the edge in any way, in any direction. It doesn't matter. Good. So given this lemma, we can lift this lemma to a setting of graphs of bounded tree. Yeah, so now I've got a graph which may be not a tree, but it has low tree width. It has tree width at most k. And imagine also there will be another generalization that I've got some subset of vertices that are interesting for me. These are those vertices S. Then I claim that I can find a small subset of vertices, a subset of at most k plus 1 vertices. It will be actually a back of a tree decomposition, such that whenever I remove this vertex, when I remove this set of vertices from the graph, every connected component has at most half of the vertices of S. So let's look at the picture. Maybe here are vertices of S somewhere in my graph. And then I claim that I can remove a small number of vertices. Here is my set S, such that in every component after removal of S, I've got at most half of the vertices of S, right? So this is a generalization of the previous fact in two directions. First of all, graphs of bounded tree width instead of trees, and second, I've got some subset of vertices that are interesting for me, not all the vertices. Okay, so the proof is essentially the same. Let's look at a tree decomposition of width at most k of my graph. So here it is. Yeah. So again, as we looked at last time, every edge of a decomposition corresponds to a separation in my graph, a separation into left, right, and center Yeah, so here B, here A, and separator X, which is the adhesion at this edge. Yes, and the A consists of all the vertices that live only in this part of the graph. B corresponds to all the vertices that live only in this part of the decomposition. And the adhesion are the vertices that are both in this bag and in this bag. So again, let me look at this edge and let me orient the edge towards the endpoint, which has more vertices of S. So the vertices of S may be in A, maybe in B, say there are more of them. Yes, there may be some in X, I don't care. So I look at how many of them are in A, how many are in B, and I orient the edge in this direction. So now, again, by the same argument, there is always a vertex without degree 0 toward such that all the edges incident to this vertex point towards this vertex. So now the back of this vertex, let's call it this vertex X. So now I claim that when I look at the back of this vertex, this has size at most k plus 1, because I assume that the decomposition has width at most k, then this set X is good. Yeah. Why so? Because every connected component of my graph after the removal of X must either be entirely contained here, or entirely contained here, or entirely contained here, or entirely contained here, in the sense that all the vertices can live only in those bags. And whenever we were orienting those edges towards the middle back, we were always orienting them from the part that has less vertices of S, which in particular has at most half of the vertices of S. So this is just a basic lift of this notion, and such set X for a set S of vertices of interest we are interested in is called a half balance separator for S. Right. So this was this lemma about the half balance separator. Are there any questions? Maybe some plus ones if you are content with this proof. I don't see too many plus ones. Are there any doubts at this point? Okay, maybe I will continue because the number of plus ones is also not that small. Good. So I have now the proof that if my graph has small treewidth at most k, then I can always find a small balance separator. Every set vertex set in my graph can be shattered shattered into pieces of size at most half by a small set. I will actually need a little bit more. I will need a 2/3 balance separation instead of a separator. So a separation is, as we already seen, a partition of the vertex set into A, X, and B into left side, right side, and the separator, such that there is no edge between the left side and the right side. So the whole communication goes through the vertices of the separator. Such a separation is 2/3 balanced for my set S if I see at most 2/3 of vertices of S on the left side and at most 2/3 of the vertices of S on the right side. So now I would like not to have just the separator and every connected component to be small. I actually want to have a separator together with a partition into left and right, so that I do not have all the vertices of S on one side. So I claim, and this is an easy lemma that we will prove in a moment, that if I have a half balance separator, I can turn this half balance separator into a 2/3 balance separation. Yeah, so I will lose a little bit on this separability, but I will be able to have the part after the removal of the separator to be divisible into left and right. So the proof is actually pretty simple as well. So we've got a half balance separator. So the situation looks like that we've got a set X, yes, of size, not of size, but that such that every connected component, C1, C2, up to some Ck, it contains at most half of the vertices of S. So now the idea is that we need to partition those components into A and B so that in each of those parts of the partition, there's at most 2/3 of the vertices of S. So for every part Ci, let me write this number, small ci, which is the fraction of the vertices of S that are contained in this part. So for instance, if I had 100 vertices of S in total and C1 contained 10 of them, then this corresponding fraction would be 1/10. So what do we know about the small number Ci? Well, first of all, they must be at most half. Each of them is at most 1/2. Well, because I had a half balance separator. And second of all, together they add up to at most S, and at most because there might be some vertices of S inside X. So the sum of all the Ci's is at most 1. So now this is a very easy combinatorial fact that if you've got numbers that are all at most half, and they sum up to at most 1, then you can partition them into 2 groups such that in every group, the sum is at most 2/3. And to see that actually I need to have here 2/3 instead of 1/2, consider the corner case 1/3, 1/3, 1/3. Yeah, all of them are at most half, but in order to partition them into 2 groups, I need to allow each group to have a size at most 2/3, total sum at most 2/3.
I've got a question to the definition of the partition. I've got a question. I mean, previously we assumed that we assumed that X should have at most k plus 1 elements. And do we assume it here too?
Yes, meaning I wrote this lemma in a concise way, maybe not putting all the details. What I mean by this is that
I'm not talking about the lemma. I'm talking about the definition.
It's a 2/3 balance separation.
Yeah.
You mean, yeah. So in the definition, we formally do not assume something about the size of X. However, what we will conclude is that there is always a 2/3 balance separation where X is of size at most k plus 1.
Okay.
Yeah, thanks. Good. So where were I? I was proving this fact. Yeah. Ci's are at most half. They sum up to at most 1. I can partition them into 2 groups with each group summing up to at most 2/3. So let me order the Ci's from the highest to the lowest. Yes, C1, C2, C3, and so on and so on. So I put it graphically by drawing those intervals with a particular length. So these all these intervals, they sum up to the length at most 1, right? There can be some slack here. So let me put here a peg at 1/3, at 1/3. And how I will partition into 2 groups, the first group will be this peg 1/3 rounded up. So this is the first group. And the second group is this, the rest. Yeah. So clearly the rest has total sum at most 2/3. Yeah, because, well, I've put at least 1/3 to the first group. So now I need to argue that the first group is also of size at most 2/3, of total sum at most 2/3. And this is kind of clear on this picture, where this peg of 1/3 falls not into the first interval, yeah, because the second interval and every further interval is smaller or equal than the first one. So if my peg 1/3 was not put in the first interval, then the first interval is of length at most 1/3. So this interval, this rounding error that we get here, has to be at most of size C2, which has size at most C1, yeah, which is at most 1/3. So I can pass this 1/3 by at most 1/3 more, which means that in total I've got at most 2/3 here as well. So there's another corner case when this peg 1/3 falls into the first one. Yeah. So the first group consists only of the first interval. However, then it is actually trivial, yeah, because we have this assumption that all of those guys are of the Ci's are at most half, which means that the whole first group is actually of size at most half in total, and we are done. Good. So this was an easy lemma. So as a corollary of these two things is exactly what Jerzy was talking about, that by combining these two lemmas, I can prove the following corollary. So if I've got a graph of Treewidth at most k, I can find in it a half-balance separator that is of size at most k plus 1. And from it, I can find a 2/3 balance separation. Yes, which is a partition of the vertex set into A, X, and B, such that there is no edge between A and B. The separator is of size at most k plus 1, because that's the same separator that we had from the half-balance separator. Yes, and each of the sides, both A and B, has at most 2/3 of the vertices of S. Good. So this is a corollary that is immensely important for working combinatorially with graphs of bounded truth, because it nicely shows you that whenever I've got a graph of bounded truth, I can, and a subset of vertices of this graph, I can somehow break the subset of vertices in a balanced way. And this is used many times in different contexts when working with graphs of bounded truth, and we will use it in a moment in order to design our approximation. Good. Any further questions at this point? And if not, then please put a +1 so that we are on the same page. Okay, good. So now recall that what we are trying to do, we are trying to make an approximation algorithm for Treewidth, which is an algorithm that is given a graph together in integer k. It either tells Treewidth is too large, or it gives you a tree decomposition of width at most 4k plus. So as usual with recursion, we will be working with a more general problem. That will be the problem that we will be solving through recursion. So the subproblem that we will be working with is the following. I'm given a subgraph H. It's an induced subgraph of my graph, together with a subset of its vertices. Let's call it S. And this is not a coincidence that I use S for this thing. Yeah, and this set should be small. It should be of size at most 3k plus 4. Yeah. And you should imagine that this is the interface to the rest of the graph. So the whole graph G looks like that. And only vertices of S are allowed to be connected to the rest of the graph. And now my recursive algorithm is trying to decompose my subgraph H, yes, keeping in mind that S should be the interface to the rest of the graph. So what the recursive call should answer? Either it should give me a tree decomposition of this graph, subgraph H, which is a valid outcome, which is I managed to decompose this part of the graph. And because I want to somehow glue this decomposition to the remainder of the recursion, I request that this set S, this small set of guys that are interfaced to the rest, should be contained in the root bag, because I will be gluing this the outcome via this root bag. And of course, I request that the width of my decomposition of the subgraph H must be at most 4k plus 4. The other possible outcome is that the Treewidth of this graph itself is already too large. So observe that because H is an induced subgraph of G, this actually implies that the Treewidth of G is as well larger than K. So we can just exit the algorithm saying the Treewidth is too large. So if we have such a recursive scheme, of course, we can apply it initially to the whole graph, with empty set being the stuff that is requested to be in the root back, and then this gives us the outcome that we wanted in our algorithm. Good. So now we are solving this recursive subproblem. So the first step is actually to somehow eliminate this assumption that the set S is of size at most 4k plus 4. As long as it is strictly smaller, I just add an arbitrary vertex to S. Yeah, this is fine because S is only growing bigger and bigger and bigger, which means that that I get more and more. I put more and more constraints on what my algorithm should do. Yeah, because I have a larger and larger set that needs to be put in the top back. So from now on, after executing this step exhaustively, I can assume that the set S is of size exactly 4k plus 4. Yep. Obviously, when there are no more vertices to add, we already have a part of the graph that has size at most 3k plus 4. I can make a trivial decomposition consisting of just one bag. Good. So now we are at the case where, that is drawn in this picture, we've got this set of size exactly 3k plus 4. I would like to decompose this graph. So what the lemma tells us? The lemma tells us that I can break this S using a balanced separation. So I can find here a small separator, X, of size at most k plus 1, such that here on the left side and partition the rest into left and right. So left and right in such a way that here I've got at most 2/3 of the vertices of S, and here I've got at most 2/3 of the vertices of S. Yeah. So I break the interface in the balanced way. So this is more clearly drawn on this picture here. Yeah, so if my graph has Treewidth at most k, then I know that there must be a structure like that in my graph where I have a separator of size x and a partition of the rest into left and right, such that here I've got at most 2/3 of the vertices of S, and here I've got also at most 2/3 of the vertices of S. Yeah. However, I mean, this follows from the lemma that if the Treewidth was small, I should be able to see this. However, how to find such a thing, right? Because we need to do it algorithmically. So there is a kind of a cunning way to do it. So let me redraw this situation. So what the algorithm now sees is just the subgraph H together with the set S. So by branching or by trying all possibilities, I can guess what from S will go to the left side and what from S will go to the right side. So I guess a partition of S into the left side, the right side, BS, and the separator, XS. Yeah, so this is this partition. Yeah, I will try something for every such a partition. So now I would like to understand whether I can somehow extend this part of the separator that is contained in S to the rest of the graph in order to separate this part from that part. So what I do, I run maximum flow min cut algorithm to find a minimum cut that separates AS from BS in the graph after exclusion of after excluding XS. Yeah, so I try to find the maximum flow between AS and BS, which is by Menger's theorem equal to the minimum cut. Yes, so this is the set Y that I just drew. So observe now that if my set Y is pretty small, together with my guess on what happens inside S, it has at most k plus 1 vertices, then I'm actually happy because this whole thing is a separator X. The stuff reachable from AS is a valid left side, and this part reachable from BS is a valid right part. Yeah, I have just found my separation A, B, and X, yes, with exactly the properties I want. At most 2/3 of the vertices here, at most 2/3 of the vertices of S here, and at most k plus 1 vertices in the middle. Of course, I do it only for the separations with only for partitions with AS and BS of size at most 2/3 of all the vertices of S. Otherwise, it doesn't make sense. Yeah. So if my max flow min cut actually found a small separator Y that together with XS has size at most k plus 1, then I have found a separation that I want. On the other hand, observe that knowing that there exists a structure like that, I know that my max flow needs to succeed for some partition of S. So if I did not find Y for any partition of S that I have looked at, then this means that my lemma was not true, because I do not see this structure at all in my graph. And if the lemma was not true, then this must be because the Treewidth is large. Because if the Treewidth was small, I would see the structure by the lemma. Yeah. So actually, what I get from this is that the Treewidth of H is larger than K, which implies that the Treewidth of G is large. Yeah. Just on the end note, what is the running time of all this procedure of finding a suitable separation AXB? Well, we are trying 27, 27, but rather 3 power 3k plus 4 different partitions of my set S, which is order of 27 power k, and this is the factor why this 27 will come into play. And for each partition, I run a max flow algorithm, and I'm caring only about cutoff size at most k plus 1. So in order to check whether there is a cutoff size at most k plus 1 between two sets of vertices, I need to run at most k plus 1 rounds of Wolff-Ruppeson algorithm, and this gives me each of those runs is run in linear time. So I've got running time k times the size of the graph. In terms of the number of edges in a graph of bound of Treewidth k is at most k times n. So the total running time is k squared times n. Linear in n. This is the what's important. And now I do it for all the 27 power k partitions. So I need to multiply those two numbers and get running time 27 power k times n times some k squared that I do not care about. Good. So this was an algorithm for finding a partition AXB. The algorithm can fail and conclude therefore that the truth is large. Good. So any questions at this point? Yep.
Can you repeat what was our aim? Like we either show that the Treewidth is large or what? Because I can't read.
I mean, we did not finish the algorithm so far.
Yeah, but yeah. I missed at the beginning.
Yeah.
Like
so
we are given the subgraph, we are giving a subset.
And yeah, we are giving a subgraph as a subset of its vertices that sort of represents the interface to the rest of the graph. And the first possible outcome is a tree decomposition of this subgraph.
Oh, okay.
Yeah, with this interface contained in the root back. Or the second outcome can be a conclusion that the Treewidth is large.
Okay, I could not find out what TD is.
Yeah, okay. TD is a tree decomposition.
Okay.
It's a short. Cool. Yeah. Good. Any more questions at this point? This is a kind of a non-trivial part of the argument. Good. Maybe some plus ones, if you're happy. Okay. Good. Yeah. So now we can give the whole algorithm for computing this tree decomposition. So when we have already computed the separation AXB, we do recursion. We split into the left side and the right side. So the left side consists of A and X. The right side consists of B and X. So more formally, on the left side, I take a graph that is induced by the left side A and X, and I consider this whole thing, yeah. So S intersection A together with X as my new boundary, as my new set SA, and symmetrically on the left. So now, if this is my new SA, what is the size of SA? Now comes the crucial point why we were splitting this in a balanced way. The size of SA, well, it's at most the size of S intersection A. So this is this part, yeah, plus the size of X, which is this part, yeah? Which is, well, S intersection A is like 2/3 of the size of S, yes. The size of X is k plus 1, all right? This was from this balanced separator. Now 2/3 of the set of the size of S is like 2/3 And the size of S was what? Was 3k plus 4. Yeah? Plus k plus 1. Yeah? This must be integral, so I can put a floor here. And now when you look at it, this 2/3 3k plus 4 is like 2k plus, plus something, which rounds down to 2k plus 2. 2k plus 2 plus k plus 1, this is 3k plus 3. So the idea is that we have now added this separator x to the boundary of the left side. However, this addition of the set x is offsetted by removal of this missing 1/3 here. Yeah. So this missing 1/3 was transferred to this new part from x. And this is the trick. This is why we're splitting S in a balanced way in order to accommodate the increase of the boundary by the separator. Yeah. So 3k plus 3. So we actually have a slack, yeah, because we had our assumption was that S is of size of 3k plus 4. And the same here. The size of SB is at most 3k plus 3. So now we recurse. We find a tree decomposition of the left side and the tree decomposition of the right side by recursion, with this SA and SB being the boundaries. And now when we have this two tree decomposition, we can combine them into a tree decomposition of the whole graph. I put them side by side. I create a new root back consisting of S and X, my separator X. So what is the size of this root back? S union X, this is at most, 3k plus 4. This was the size of X plus k plus 1. This is the size of X. So this is 4k plus 5, which is perfect because we wanted to have width 4k plus 4, which means backs of size 4k plus 5, right? So this is my root back that I put here, and I just put the root backs of this partial decompositions obtained from recursion as the children. And it is kind of clear that this should be a tree decomposition of the whole graph. You can check it, but essentially, like every vertex of the separator that is a vertex that lives both on the left side on the right and on the right side. Yes. Well, it is also here and here in those root backs. So essentially, the subtrees in which this vertex lives on the left and on the right, they get glued by the root back. Yeah. So what's about the complexity of the algorithm? Well, we do some recursion, so we need to understand what is the total time of this recursion. So observe, and now comes another technical trick, that we obtained those sets S of size at most 3k plus 3, not 3k plus 4, which means that whenever we are making a recursive call here, the immediate next step will be adding one more vertex to S, right? Because remember that in my first step, I was adding arbitrary vertices to S as long as S was too small. So every recursive call is immediately followed by eating up one more vertex of the graph, which means because every vertex is being eaten up in the whole process at most once, there are at most n recursion calls in total throughout the whole recursive scheme. So in each recursive call, we were using this running time for all those Maxflow computations, which by multiplying this by n gives me a total running time of 27 power k times some polynomial in k times n squared. Yeah. So n times we run a linear time algorithm on the graph. This is a little bit, you can see that you probably can kick this algorithm in order to get something faster in terms of this n square. Indeed, it's not very hard to make this n square into n log n factor, but making it into a linear factor is actually a lot of pain. However, there is a 5 approximation algorithm that runs in time 2 power order k times linear in n, and this will be this is actually a pretty useful black box algorithm. Good. So this finishes the 4 approximation algorithm. Are there questions at this point? Good. Some plus ones, if you're happy. I don't see too many of them. Any doubts? Yeah. Oh, somebody is even +2. Okay. He understood this algorithm twice. Good. Good. So this finishes what I wanted to do on the previous lecture, which was the approximation. And now we move to more combinatorial results and applications of Treewidth in parameterized algorithms, in particular on planar. So first, before we continue, I would like to give you one more definition of Treewidth, namely a game theoretic definition via a so-called Cops-and-Robber game. So imagine that you've got a graph on which the game will be played, and there are k cops that try to catch one robber. So the game starts with the cops placing themselves in some vertices. So for instance, vertices like that. And the robber also places herself in some vertex. Of course, the cops would like to catch the robber. So what happens in a round of the game? The round consists of three steps. First of all, some cops decide to move. Yes, some cops will stay on the ground, some cops will move. And a move of a cop means that a cop decides that I will move, for example, to this vertex. Yes. He declares where he will land. So he lives in a helicopter, flies, and will during this round fly to this vertex and will land there at the end. Yeah. So at this point, when some subset of cops is lifting in helicopters, they are not on the ground. So at this point, when they are in the air, the robber can move, and the robber can run along the edges of the graph. Not a single edge. She can run many steps in one round, but she can only go she cannot go through the vertices on which the cops are still occupied by the cops. So, for instance, from this vertex, she can, for instance, run here and place herself here. And at the end of the round, this cop decides this cop lands in this vertex. So in the next round, for instance, this cop will decide to go to this vertex. Yes, the robber, for instance, she stays at this vertex. Then the cop lands in here, and so on and so on. For instance, maybe now this cop will move to here. Yeah, so that now robber is completely cornered in here. Yes, and now the thing is that so now, for instance, this cop can decide to go here. Yes, the robber needs to escape from here. Yes, she needs to move here. So now the situation is like that, and finally, this robber will catch the robber by landing on this vertex here. Yeah. So as you see on this graph, 3 cops were sufficient to catch the robber. The goal of the cops is to catch the robber by landing on a vertex that is occupied by her, and the goal of the robber is, of course, to evade being caught in the film. Good. Are the rules of the game clear? Are there any questions on this? So if not, then maybe I will formulate the main theorem that we have here about the Cops-and-Robber games, namely Treewidth can be defined equivalently through the Cops-and-Robber game. Namely, the Treewidth of a graph is exactly the minimum number of cops that you need in the game to catch the robber, -1, of course, because all of those -1s happen due to this +1 in the definition of Treewidth. So we will not prove this theorem fully. I will give you just one inequality. The inequality that if I have a tree decomposition of width k, then k+1 cops are sufficient to catch the robber. So this is this inequality. So I will give you a strategy for k+1 cops. So the cops place, I root the decomposition. I have a tree decomposition of width k. I root the decomposition somewhere, and the cops place themselves in the root vector. And the robber needs to decide in which part of the graph she will be. For instance, this. So now the cops will push the robber down the tree. So for instance, in this round, these two cops on the adhesion of this edge of the decomposition, they will stay on the ground so that the robber cannot escape from the subtree. And the remainder of the cops will move from this portion of the back to the remainder of the back here. Yeah. So after this round, this whole back will be occupied by the cops. And again, the robber needs to be confined in one of those subtrees. Yeah. So again, in the next round, the cops will move to occupy this back while guarding this adhesion, and so on and so on and so on. So after at most n rounds, they will actually corner the robber in one of them, in one of the leaf backs. The proof in the other direction, this is the direction that if you have a strategy for the robber, then your Treewidth must be large. You cannot have a small tree decomposition. This is much more difficult, and we will not give this proof. However, this is actually the implication that is important for us, because how we will use this theorem, observe that this theorem can be used in the following way, that if I've got a strategy for a robber, against k cops, then this implied that the Treewidth must be at least k minus 1. Yeah? So in order to give a lower bound on Treewidth, it suffices to give a strategy for the cop. And this is very useful when trying to prove that some graph has actually large Treewidth. So for instance, yeah, maybe some questions at this point about this proof. Okay, if not, then we can move to the corollaries. For instance, I can immediately say that the Treewidth of a click on t vertices is t minus 1, which is something that we did not phrase specifically in the last lecture. Why? Because the trivial, like the robber can move from any vertex to any vertex, because all pairs of vertices are adjacent. So if there are at most only at most t minus 1 cops in the graph, then she can always move from a vertex that is that was free to a vertex that is free. Another corollary that is kind of very nice is that I can prove to you now that the Treewidth of a grid is large. That a t times t grid shown here, this is t by t, that the Treewidth of a t by t grid is at least t minus 1. Why? So I will give a strategy for the robber. So if I'm having only t minus 1 cops and I have t rows and t columns, then there is always a row and a column that doesn't contain any cops, right? Because t minus 1 cops can occupy only at most t minus 1 rows and t minus 1 columns. So the strategy for the robber is to always be on the intersection of a free row and a free column. So now what happens when the cops move? Well, some of them live in their helicopters deciding where they will land, but after they land, there will be still some row and some column that is free. Right, and during the time when the robber, when the cops are in the air, all those rows and columns are free. Those green ones are free because they were free before, and the violet ones or the pink ones are free because they will be free after landing, right? So at this point, the robber can freely move to the new intersection of a free column and a free row. So this gives you a strategy for a robber against t minus 1 cops. Yeah? You can give a strategy for the cops for t cops. No, sorry. You can give a strategy for t plus 1 cops. This is the strategy that is usually that gives you a tree decomposition. So t plus 1 cops can like sweep the grid by moving one vertex at a time like that. Yeah, so they sweep the grid from left to right while restricting the area for the robber. And this corresponds exactly to a tree decomposition of a grid that sweeps the grid from left to right. So this proves, both of these things prove that the truth of a t times t grid is between t minus 1 and t. Actually, it is equal to t. You need to devise a slightly smarter strategy for the robber. A robber can win not only against t minus 1 cops, she can even win against t cops. And this gives you a tight bound for the truth of a grid. Good. Any questions at this point? Maybe some plus ones if you are happy. Any doubts? Okay, let's move further. So yeah, this brings us to the question: how do you actually witness, certify that the truth of a graph is large? One thing is to try to devise a strategy for the robber. It's not a really well-behaved combinatorial object. You can actually define it, but we will not delve into this. We have actually already seen some way of witnessing that the truth of a graph is large, namely why our approximation algorithm failed. So I claim that from our approximation algorithm, the following statements follow: that if my graph has large truth, if the truth is larger than 4k plus 4, then there must be a set of vertices S that cannot be broken in a balanced way. Yeah, a set of 3k plus 4 vertices, such that for every separation with the separator being of size at most k plus 1, either the left side or the right side of the separation contains more than 2/3 of the vertices of S. Yeah, so the situation is that if I've got my set S in my graph and I try to break it using a small separator, at most k plus 1, I cannot break it in the balanced way. There must be a side that is large and a side that is small. So I claim that if my truth is large, then actually there must be such a set S. Why? Because let's run our approximation algorithm on this graph, and the only way the approximation algorithm can conclude that it fails is by exposing such a set. So if there is no such a set, then the truth must be small, no? Because the approximation algorithm succeeds. Good. And of course, if you've got such a set S with these properties, then this is a contradiction to our lemma about the Treewidth K graph. So if there is no such S, if there is such an S, then the Treewidth of my graph is large. This set S witnesses that the Treewidth is large. And this is exactly our lemma. So in this sense, such a set S, which is usually called a well-linked set, is a certificate that is always present, that certifies on one hand that the truth is large, and is always in some sense contained in a graph where the truth is sufficiently large. Yeah, with the largest k for which such a well-linked set exists not being exactly k, but roughly k. Such a well-linked set, they are very useful. However, they are a little bit unwieldy. We would like to understand a little bit better how to witness that the truth of a graph is large. Okay, so one way to look at it is the following. Obviously, if I've got a subgraph of a graph, then the truth is not large, because I can just throw away some vertices, throw away some edges, and this gives me less to embed and less constraints on the embedding. Yeah? So obviously, this means that if in a graph I find a click on t vertices, then the truth must be at least t minus 1. Yeah, because this graph alone has large truth, so any graph that contains it must have a large truth as well. And the same for grids. If I have a grid as a subgraph in my graph, then the truth of the graph must be large, at least as large as the truth of a grid. So finding a embedded graph in some sense of large truth witnesses that the truth is large. This is a kind of an obvious statement, but bearing in consequences. We will actually not work with subgraph embedding. We will work with minor embeddings. I hope that many of you have already seen minors here or there, but let me introduce them formally. So this is an embedding notion for graphs that is kind of suited for different topological reasonings. So I say that a graph H is a minor of a graph G. If I can find a minor embedding, a minor model, so-called, of H in G, and the minor model looks as follows. Every vertex of H must be mapped to a connected subgraph in G. These subgraphs should be disjoint, and there should be preservation of edges. In the following sense, whenever I have an edge here, there should be an edge between the corresponding subgraphs. So you can imagine, and these subgraphs should be connected. Yeah? So you can imagine that every vertex of my graph H is being smeared into a connected stain of vertices here, so that whenever I've got two adjacent vertices on the left, the stains onto which the vertices are smeared should be adjacent. Yeah, so this is kind of a topological way of embedding one graph into another. Yeah? So obviously, if H is a subgraph of G, then of course it's also a minor, because I can just smear onto one vertex stains, right? H is a subgraph of G if you can obtain H from G by removing vertices and removing edges. So you have a similar operational definition for minors. Namely, you can, H is a minor of G if and only if H can be obtained from G through the following three operations, either vertex deletion or edge deletions. These are the usual subgraph operations, and also edge contractions. So the operation of contracting an edge looks as follows. So imagine that here is an edge. This vertex has some neighbors, this vertex has some neighbors. Maybe they have some common neighbors. Yes. So then contracting this edge here means that I replace these two vertices with one new vertex that is adjacent to all the vertices that these two vertices were previously adjacent. So whenever they had a common neighbor, this common neighbor is now adjacent to this new vertex. And this is an edge contraction. I guess it's kind of a natural operation. And then you can prove exactly this fact, that H is a minor of G, and only if you can obtain H via those three operations. The proof in one direction is very simple. If you have a minor model like that, then what you do, you just remove all the stuff that is here, not participating in those stains, and you just contract every stain into a single vertex because it's connected. So you can contract it along a spanning tree. On the other hand, if you have this contraction sequence that yields you my graph H, yeah, for instance, the graph H looks like that. You can now think of undoing the contraction. So, for instance, at the last moment, this vertex was obtained from contracting two vertices. So the situation might have looked like that. Yeah. So now when I'm contracting this vertex, I imagine that this is my stain that corresponds to my vertex that was here before. And then when I proceed with those uncontractions, at the end I get for every vertex a connected stain. These stains must be disjoint, and they should be connected appropriately by edges, because at the end I got those edges there. Good. I hope that this was a kind of a sketch of a proof. However, this fact is very easy to visualize, so I hope that you are fine with that. Good. Are there questions at this point? Maybe some plus ones to get more confidence. Good. Yeah, this is basic graph theory and structural notions. So I hope that there was nothing too difficult happening. So now the basic observation about Treewidth is that Treewidth is minor closed. It's a minor closed parameter, in the sense that if I've got if H is a minor of G, then the Treewidth of H is at most the Treewidth of G. Yeah, taking a minor cannot increase the Treewidth. So by this fact that we had here, about this operational definition, it suffices to check that none of those operations increases truth. Because, well, then we do a sequence of those operations and the truth can only decrease during those operations. So for vertex deletion and edge deletion, this is clear, yeah, because I just have less vertices to embed, or I have less constraints that I need to obey when defining the bags. So the previous tree decomposition is also a decomposition after the operation. For edge contraction, this is a little bit more tricky. So imagine that you are contracting this edge here. So now it is actually useful to think of this tree embedding. So for instance, the subtree corresponding to the blue vertex looks like that. And the subtree corresponding to the, I think, orange vertex looks like that. Yeah. Now these two subtrees, they need to intersect somewhere because there was an edge. There must be a bag containing both of those guys because there was an edge here. So now, after the contraction, I make a new decomposition of my graph. I keep all the subtrees the same, apart from, of course, the subtrees corresponding to the blue vertex and the orange vertex, which are now contracted to a green vertex. I use for the green vertex a subtree that is the union of the previous blue subtree and the previous orange subtree. Now, this is a connected subtree because those two subtrees actually intersected because of the existence of an edge. And it is kind of easy to see that that this doesn't increase the width of a decomposition, yeah, because the only thing that can that could happen is that I replaced in some bags either U or V with this new vertex W. Yeah? So the sizes of the bags could only decrease because I substituted one or two vertices with just one vertex. Good. So this means that if a clique is a minor, if I find a large clique as a minor, then my truth must be large. And if I find a large grid as a minor, then my truth must be large. Yeah. So so both a clique minor and a grid minor are sort of witnesses, certificates that the truth of a graph is large. However, are there sort of sufficient certificates? In the sense that if I have a graph of large Treewidth, does it necessarily contain a large clique minor? Or if I have a graph of large Treewidth, does it necessarily contain a large grid minor? So the answer to the first question is actually no. I may have graphs of very large Treewidth and no K5 as a minor. And this is because of Kuratowski theorem, Kuratowski-Wagner theorem. Kuratowski-Wagner theorem says that planar graphs are exactly graphs that are K5, K3, 3, minor 3. Yeah, so graphs that do not contain K5 or K3, the biclic K3, 3 as a minor. And observe that a grid is actually planar. Yeah, so it doesn't contain K5 as a minor. However, it has arbitrary grids have arbitrary large trees. So yeah, the question now is about grids. Is it the case that if I have a graph of very, very, very large Treewidth, does it necessarily contain a large grid minor? Is this obstacle always there if the Treewidth is large? And the surprising answer is that this is actually true. And this is one of, I think, main results of structural graph theory, of modern structural graph theory, the excluded grid minor theorem, which says that there is a function f such that if the truth of the graph is at most f of t, so it is sufficiently large in terms of t, then I will be able to find a t times t grid as a minor. So conceptually, this means that the only way a graph does not look roughly as a tree is because it contains a large bidimensional object. A large bidimensional object expressed as a minor of a large grid. And this is a conceptual dichotomy in graphs. Yes, either they are simple because they have small Treewidth, or they contain large bidimensional object. And we will be able to use this dichotomy algorithmically in a moment. Good, but before we go further, maybe some questions now about the excluded grid minor theory and whatever we did before. Good. Are you happy with that? Plus ones, please. Yeah, good. So before we continue, let me make some notes about this theorem. This is an immensely important result. It was proved in the first proof was in the 80s by Robertson and Seymour in their graph minor series. Then the proof was the initial function f was even not explicit. It was not sure whether it's computable. Then there were more explicit proofs. In particular, in the book of Distal, there is a nice proof with upper bound f of t, I think 2 to the order of t to the 5. And this is a proof that we teach on the course selected topics in graph theory next semester. And it was a very, for a long time, it was an open problem whether you can give a polynomial upper bound. And this was proved by Chandra Chekuri and Julia Trujoy in 2012, as far as I remember. Chekuri and Trujoy, which gave a polynomial bound. Yeah, the currently best upper bound is t to the 19, as far as I remember, with some polylogarithmic factors. The best lower bound on how large the Treewidth must be in order to certify a grid is t squared of t. And people actually believe that this is the answer. The left side is the answer, up to maybe some polylogarithmic factors. The proof is difficult, even of this exponential bound. Essentially, what you do, you know that if the Treewidth is very large, you start you find a large well-linked set in your graph, and once you start with this well-linked set, you can get some from Menger. You can get some paths through flows, and you can start to weave your grid. But there's a lot of technical details when making this grid. So now we will make an application of this theorem into the cycle packing problem. So the cycle packing is a very nice problem. You are given a graph G, an integer k. And the question is whether in your graph you can find k vertex disjoint cycles. So cycle number 1, cycle number 2, cycle number 3, cycle number 4, maybe cycle number 5, maybe cycle number 6. Yeah? So vertex disjoint in the sense that they cannot share any vertex. So now my goal is to prove to you that in 3 lines that this problem is fixed parameter tractable when parameters by k using the grid minor theorem. So first of all, I will run my approximation algorithm for Treewidth. For t being this magic number, f of 2 square root k, where f is this function from grid minor theorem. Yeah. So I test whether the graph has large Treewidth or small Treewidth. So first of all, it can happen that the Treewidth is large. My algorithm.
Excuse me, can you show the goal again? Okay.
Given a graph, I would like to test whether there are k vertex disjoint cycles, whether I can find k vertex disjoint cycles in this graph. Okay. So I run my approximation algorithm. There are 2 possible outcomes. Either the Treewidth of the graph is large, or the Treewidth of the graph is small. In case the Treewidth of the graph is larger than f of 2 square root k, then from the grid minor theorem, I get a large grid. I get a 2 square root k times 2 square root k grid as a minor. Yeah, so this is this grid minor that is here on the left. And then I claim that this immediately implies that I can find k vertex disjoint cycles in my graph. So let me just draw them. Yeah, in each 2 by 2 square in my grid minor, I can find a cycle connecting those four connected subgraphs, and in this way I can get square root k here, square root k here. So I got k vertex disjoint cycles. Square root k may not be integral. Please put the ceilings as you wish somewhere here in this argument. Good. So this means that if the Treewidth is large, then I immediately get a yes answer, which leaves me with the second case, the case when the Treewidth is small. Namely, I got from my approximation algorithm a tree decomposition of a small width at most 4 times this magic number plus 4, which is just some function, say h of k, right? So now what I can do, I've got a tree decomposition of small width of my graph. So I can apply dynamic programming. So if I'm lazy and I do not care about the time complexity, I could just use Kurzweil's theorem by saying that the cycle packing problem is expressible in monadic second order logic, because I can just say there is the first cycle, there is the second cycle, there is the k cycle, because my formula length can depend on k, and I check whether indeed each of them is a cycle. And so from Kurzweil's theorem, I can get an algorithm with running time, some function of the width of the decomposition, which in turn is a function of k, and k, which is the length of my encoding of the problem. If you do not like Kurzweil's theorem and you want to design your own dynamic programming algorithm, it is not hard to get this to run in time, probably something like 2 power w log w times k power w, I guess, times n. This would be the running time of your algorithm if you design it by hand. Yeah, you need to remember like matching cycle for a Hamiltonian cycle, plus you need to remember which vertices of the back are in which cycle. But because k is because w is a function of k, all in all, I've got this running time for approximation of Treewidth, and then this running time for running the dynamic programming, which gives me some function of k times n square running time. So now you actually see why I was so delving so much about this n square here, because if we do it like that, we actually have n square here, because in terms of n, the bottleneck is the approximation algorithm. So getting this down to n means that this can be brought down to n as well. Good. So this is a classic application of this called the win-win approach. Either the Treewidth is large and we have immediately an answer, or the Treewidth is small and we can run a dynamic programming. And this is a very classic technique in parameterized algorithms. Good. Any questions at this point, or some plus ones to make sure that we understand? Okay, good. So let's see where we can apply the same principle. So this essentially works for all problems that are so-called bidimensional. And bidimensional is not really well-defined notion, but essentially this means that if there is a large grid in my graph, then I have a certain yes or no answer. Yeah? So for instance, this works for cycle packing because we've got those cycles. It would also work for k-path problem, where I want to find whether in my graph there's a simple path on k vertices. Why? Because if I want to check that this graph, that if I have a square root k times square root k grid, then I've got a k path, I can only draw a snake looking like that. Yeah. So the existence of a large grid minor certifies that there is a k path. But this will also work whenever the existence of a grid gives me a certain no answer. So for instance, if I am working with vertex cover problem, I would like to check whether the edges can be covered by at most k vertices. Exposing a square root k times a square root k grid exposes also a matching of size k. Yeah, and expose of say size larger than k. And exposing a matching of size larger than k tells me that my vertex cover instance is actually a no instance. The answer is no, because well, I would need one edge to cover each of those edges. Yeah, and similarly for feedback vertex set. For instance, I can then expose those cycles like in cycle packing. So if I'm solving a feedback vertex set, I can immediately say that if there is a large grid, then the answer is no, because I would need to hit each of these cycles separately. Good. So this is a basic technique. However, it will not give you the right running time in general. Well, for feedback vertex set, we have seen a 5-power-k algorithm some few lectures ago. This technique, if you applied it, would give you at the best something like 2-power polynomial in k, which is far worse than what we can do with a hand-written algorithm. However, the technique is general. Good. So, however, this technique actually becomes surprisingly powerful when we are looking at planar graphs. So, in planar graphs, the grid minor theorem is much better, in the sense that if I have a planar graph that has large Treewidth more than 9/2 times t, then it must have a grid, t times t grid as a minor. So recall that in the grid minor theorem, this was this f of t. Yeah. So this means that in planar graphs, the f of t, the dependence between the grid minor and the Treewidth, is actually linear, and we will this will be important in a moment. I will not prove this fact again. However, I think it is nice to understand where this grid comes from. So how you prove this theorem, you make an approximation algorithm for Treewidth, trying to decompose the graph, and the approximation algorithm works similarly as before. So it tries to decompose some subgraph drawn here of my planar graph. And the thing is that the boundary of this subgraph, this set S, it will be always of length of size at most 4t. And it will be like a curve in the plane. Yeah, so there will be some cycle, some circuit in the plane that will embed some closed curve in the plane that will enclose some part of the graph, and this S, the set of vertices on this curve is my set S, that is the boundary, and I would like to decompose whatever is inside. So if my boundary is of size at most 4t, I will break it into 4 pieces of length t and call them north, east, to southwest. And now I would like to proceed with decomposing the graph. So if you, for instance, one way of decomposing the graph is to find a small cut between north and south. So to find at most t vertices here that that cut the west from the east. And by planarity, you can argue that actually this looks like, you can choose it as a curve going from north to south of length at most t. And then you can proceed as in our approximation algorithm, namely to solve this part separately, decompose this part separately, decompose this part separately, and glue together the results. And the trick is that if you had t vertices here on the west, yes, when looking at the right part, you replace them with the t vertices on the separator from north to south. Yeah? So you can find a separator between west and east of small size and recurs, or you can find a separator between west that separates north and south, and then recurs on the lower part and the upper part. Or if you cannot find any of this situation, then by Menger's theorem, you can find a flow of t paths from west to east and a flow of t paths from north to south. And this kind of looks familiar already, right? So this is where the grid comes from. Actually, the argument technically is more involved because, for instance, this path might look like this. So it doesn't necessarily give you the grid right away, but you can kick this argument a bit and get from 2 crossing flows a grid as a minor. Good. So this was a sketch of a proof of the grid minor theorem for planar graphs, which has a linear dependence of the Treewidth on the grid size of the Treewidth on the requested grid size. And we can get some very nice and a lot of corollaries of this fact. So one corollary is that actually, if I have a planar graph on n vertices, then the tree-width of this graph is square root. The tree-width of an n-vertex graph is order of square root n. Why? Because if it was larger than 9/2 times square root n plus 1, then by grid minor theorem, we would see square root n plus 1 times square root n plus 1 grid, which means that I have more than n vertices in my graph, but I assume that there are n vertices in my graph. This was the definition. Yeah. So just by counting the number of vertices, I could not squeeze a larger grid there. Yeah? So this means that the tree-width of an n vertex graph is square root n. You can approximate this tree-width, no problem for approximation algorithm. So for instance, if you approximate the tree-width and then run our 2 power t times t power order 1 times n algorithm for max independent set, then this algorithm runs in time 2 power square root n, order of square root n. So max independent set, free coloring, vertex cover, feedback vertex set, and so on, they all can be solved in running time 2 power square root n. Actually, for feedback vertex set of Hamiltonian cycle, this is a little bit, if the standard dynamic programming works in time t to the order of t, yeah, times n, which translates to n power square root n using this technique. Yeah, you need to work a little bit more to get rid of this n in the base, but it can be done in case of planar graphs. Right. Any questions at this point?
Where does this 2 to the O square root n complexity come for these algorithms?
So for maximum independence set problem, I've got a 2 power Treewidth algorithm times n. I know that the Treewidth is order of square root n in a planar graph. So I just approximate the Treewidth and run my dynamic programming.
Okay, thank you.
Yeah. Any more questions? Good. Maybe some plus ones to make sure that we are happy. Okay. Yeah. So actually, here we have designed like a exponential time algorithm. So in general, the natural algorithm in general graphs for max independence set problem runs in power 2 power n in time 2 power n, and you can refine this n in the exponent to square root n in case of planar graphs. But you can also apply the same technique to parameterized algorithms. For instance, for cycle packing. I claim that cycle packing can be, in parameterized sense, solved in time k to the order of square root k times n, where k is the requested number of cycles. And this is the same principle that we did before with the bidimensionality. So I approximate the Treewidth for this parameter, which is the threshold for existence of a 2 square root k times 2 square root k grid. If my approximation algorithm tells me that the Treewidth is larger than that, then I get a 2 square root k times 2 square root k grid as a minor. And then yes, I see k disjoint cycles in my graph. Otherwise, what I have is that the Treewidth, I've got a tree decomposition of my graph of width bounded by what? Bounded by, let's say that we run the 5 approximation algorithm, say 5 times this 9/2 times 2 square root k, which is order of square root k. So we've got a really narrow tree decomposition of width square root k. So now if I run my dynamic programming, which runs in power in time t power t times n, order of, then by plugging in t, by plugging in the width being roughly square root k, I've got running time of this form. Yeah. So here, this win-win is really on a very low level of the width. Yes, it's already if I have width more than square root k roughly, then I have a certified yes answer. And otherwise, my dynamic programming runs really fast because I have a tree decomposition of very low width. So the same principle can be applied to all the problems that we were talking about before. A vertex cover, yeah, where a large grid certifies and no answer. Feedback vertex, the same. Yeah, Hamiltonian cycle, not really, because that's not a parameterized problem. Say k-path, yeah, because again, existence of a square root k times square root k grid as a minor gives you a k-path. Yeah, so all these problems can be solved in time either to the square root k times n or k to the order of square root k times n, depending on the dynamic programming algorithm on bounded Treewidth graphs that you have. So it is a little bit more tricky with other problems. For instance, the independent set problem, parameterized by the solution size. Because then you need to argue. So in the independent set problem parameterized by the solution size, you just ask whether the input graph contains k disjoint, k vertices that are pairwise non-nudges. Yeah, and then you need to argue that if you have a square root k times square root k grid, then you have a then you will have an independence of size of set of size k. So you will have a yes answer. Yeah. So and this is not entirely clear from the beginning. So imagine that you've got a planar graph with a 3 square root k times 3 square root k grid as a minor drawn here, and I would like to argue that it has a large independence. Why so? Let me pick one. Let me divide this grid into 3 times 3 pieces. There is square root k times square root k of them. Yeah, and in each piece, let me pick any vertex from the middle subgraph, like that. And I claim that this must be an independent set. These vertices should not be adjacent. Yeah. However, this is not entirely clear at the beginning. Well, it's kind of clear on the picture. However, you could imagine that in your graph, there is actually an edge looking like that. It's just that in this drawing, it is not planar. But maybe I can fold this grid in a different way, draw it in the plane in a way that actually is able to embed this edge. Yeah? So you need to argue that actually these guys are non-adjacent in your graph in order to certify that they form an independence. And usually when trying to prove that something is non-planar, the easiest and the cleanest way is to highlight a minor of either K5 or K33. So here I could, for instance, take this one to be my first element of my minor, here another one. Then let me draw here, yeah. And here. So these are already 4 of them. And one more. Yeah. So if I now look at those, the union of those blue, light blue, red, green, and yellow guys, on the picture, you can see that each of them is neighboring each other. I need a bit more here. Yeah, like that. Which means that this is a K5 minor. So this red edge could not be here. Yes, because if this edge, if those 2 vertices here and here were adjacent, then I would be able to expose a K5 minor in a planar graph, which is a contradiction. Yeah. And observe that in here, I really need this assumption of being planar. Because if, for instance, I start with G being a complete graph, then obviously a complete graph contains a large grid as a minor. However, it doesn't have an independent set of size k. It doesn't even have an independent set of size 2. Yeah. So I need to use planarity in order to certify that some connections are not present. So again, by the same principle, I approximate Treewidth. approximate Treewidth. And if that Treewidth is larger than, say, 100 square root k, then this means that yes, I am able to find an independent set of size k by this argument. Or if the Treewidth is at most 100 square root k, then what I do, I run dp on a tree decomposition. Right. So it's again the same principle. And the same can be applied, for instance, to the independent set problem, to the dominating set problem. You can argue similarly that if I take those vertices, then they cannot be dominated by less than k vertices. So a large grid certifies you that, the answer is no, and so on. Okay, I see that I have just run out of time. There is one more technique that I would like to tell you about using the Baker's technique and the radius bound on the Treewidth. But maybe I will just steal the first 20 minutes of the next lecture from Marcin, and we will use this technique as well, apply this technique as well, because I think it's worth seeing. Good. Are there any questions at this point? This concludes what I wanted to talk about today.